Hello there, and welcome to Deep Sleep Seas. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're the kind of person who finds rest not in silence but in stories of the deep, in quiet tales of creatures that live where sunlight meets salt water. Either way, you've come to the right place. Tonight we're diving to the reef floor, to a world painted in colors you might not believe could exist beneath the waves. We're going to meet some of the ocean's most magnificent residents, creatures that have lived in these shallow tropical waters for millions of years, growing slowly, breathing light, and painting the seafloor with living rainbows. We're talking about giant clams, the gentle giants of the coral reef, bivalves so large and so luminous that they seem almost impossible. Before we begin, if you find these stories soothing, consider subscribing so you don't miss future journeys into the deep. And if you're still awake at the end, let me know where in the world you're listening from. I read every comment. Now let yourself settle in. Let your breathing slow, your shoulders drop, your mind drift to warmer waters. We're not in a hurry. There's nowhere to be but here, floating gently above the reef, watching as the clams open their shells and reveal their colors to the sun. Giant clams are not just large. They are spectacularly, almost impossibly large. The biggest of them all, Tridacna gigas, holds the title of the largest living bivalve mollusk on Earth. Imagine a shell that could measure more than 4 feet across, a creature so heavy that a full-grown adult might weigh well over 500 pounds, with some historical specimens tipping the scales past 700 pounds. These are not the small clams you might find nestled in sand at low tide. These are monuments of the reef, living sculptures that anchor themselves to the ocean floor and stay there for the rest of their lives, sometimes for more than a century. One of the most famous specimens ever discovered was found in the early 1800s off the northwestern coast of Sumatra. Its shells measured nearly 4.5 feet across and weighed over 500 pounds. Those shells now rest in a museum in Northern Ireland, a testament to just how large these creatures can grow. Another giant was discovered in 1956 near the Japanese island of Ishigaki. Though its shell was slightly shorter at just under 4 feet, it was even heavier, weighing in at more than 730 pounds. These record holders remind us that the ocean is capable of producing life on scales that dwarf our expectations. But Tridacna gigas is not alone. There are 12 recognized species of giant clams, all belonging to the subfamily Tridacnae. They span across the Indo-Pacific region, from the warm waters surrounding Australia's Great Barrier Reef to the scattered islands of the Philippines, Indonesia, and beyond. Some species are smaller, though still impressively large by most standards. Tridacna crocea, known as the boring giant clam, actually burrows into coral rock, creating a permanent home for itself. It's smaller than its giant cousin, but it compensates with stunning colors and an ability to thrive in places other clams cannot. Tridacna maxima, the elongate giant clam, has the widest distribution of all the species, found from the Red Sea to French Polynesia. Tridacna squamosa, the fluted giant clam, is recognized by the dramatic scalloped edges of its shell, ridges that ripple outward in waves of calcium carbonate. And then there's Hippopus. Hippopus, the horse's hoof clam, which looks almost as if someone took a giant clam and compressed it into a rounder, more compact shape. Each species has adapted to slightly different habitats, different depths, different levels of wave action and light, but they all share the same basic form, the same heavy shells and soft exposed mantles that glow with impossible colors. The shells themselves are marvels of biological engineering. They're made of calcium carbonate, the same material that forms coral skeletons and seashells around the world. But the way giant clams construct their shells is particularly remarkable. The calcium carbonate is laid down in layers, creating a structure that is both incredibly strong and surprisingly light relative to its size. Scientists have discovered that embedded within these hard crystalline layers are softer organic particles that actually strengthen the shell, preventing cracks from spreading and making the structure more resilient to the forces of the ocean. The shell grows throughout the clam's life, adding new layers at the edges, expanding outward in a slow but steady accumulation of mineral. Growth rings form, much like the rings in a tree, and by examining these rings, scientists can estimate the age of the clam and learn about the environmental conditions it experienced over its lifetime. The isotopic ratios of oxygen in the carbonate and the balance of strontium to calcium can reveal historical sea surface temperatures, turning each shell into a living archive of climate history. The weight of a giant clam is deceptive. The soft body of the animal, the actual living tissue, accounts for only about 10% of the total weight. The rest is shell. This means that the fleshy part of even the largest clams is relatively modest in size, a fact that has made them a target for harvesting over the centuries. The adductor muscle, the powerful muscle that pulls the two halves of the shell together, is particularly prized in many cultures as a delicacy. It's firm, slightly chewy, and rich in protein, considered a culinary treasure in places like Japan, France, and throughout Southeast Asia. But the lightness of the actual body also means that giant clams are efficient creatures. They don't need to support vast amounts of tissue. Instead, they invest in that protective shell and in the symbiotic relationship that allows them to thrive even in nutrient-poor waters. Giant clams are found exclusively in the Indo-Pacific region, a vast expanse of tropical and subtropical ocean that stretches from the eastern coast of Africa to the western shores of the Americas. They live in shallow waters, typically no deeper than about 65 feet, though they are most commonly found much closer to the surface, in depths of just 10 to 30 feet. This shallow habitat is not a coincidence. Giant clams need sunlight. They need it desperately, in fact, because the algae that live inside their tissues require light to photosynthesize. Without access to strong, consistent sunlight, a giant clam cannot survive. So they settle on coral reefs, on reef flats, in sandy lagoons, on slopes where the water is clear and the light penetrates easily. They nestle among coral heads, anchor themselves to rubble, or, in the case of the boring clam, carve cavities into solid coral rock. The Great Barrier Reef is home to several species of giant clams. So are the coral reefs of Papua New Guinea, the Solomon Islands, and Fiji. They're found around the islands of Indonesia and Malaysia, off the coasts of Thailand and the Philippines. In the western Pacific, they reach as far north as the Ryukyu Islands of Japan and as far south as the northern coast of Australia. In the Indian Ocean, they're present around the Maldives, the Seychelles, and along the coasts of East Africa, though in smaller numbers and with more restricted ranges than in the Pacific. Each location offers slightly different conditions, different water temperatures, different levels of wave action and sediment, and the clams have adapted accordingly, with populations showing subtle variations in size, color, and shell shape depending on where they live. These are creatures of stillness. Adult giant clams do not move. Once they settle on the reef, typically within the first few weeks of life, they remain in that spot for the rest of their days. They have no ability to uproot themselves and relocate. They cannot flee from predators, cannot migrate to better feeding grounds, cannot escape unfavorable conditions. This sessile lifestyle is both a strength and a vulnerability. It allows them to invest energy into growth and reproduction rather than movement. But it also means that the choice of settlement site is critical. A clam that settles in a place with poor light, unstable substrate, or heavy sedimentation may struggle to survive. Those that choose well, however, can live for a century or more, growing slowly but steadily, becoming part of the reef itself. If you were to swim over a healthy coral reef in the Indo-Pacific and look down, you might see them scattered across the landscape. Their shells, when closed, are rough and encrusted with algae, barnacles, and small corals, blending into the reef around them. But when they open, when the two halves of the shell gape apart and the soft mantle tissue extends outward, they become something entirely different. They become living stained glass windows, glowing panels of color that shimmer and shift in the filtered sunlight. And that is where the real magic begins. The colors of a giant clam are among the most stunning sights in the ocean. Electric blues, iridescent greens, deep purples, golden yellows, and vibrant oranges all swirl together across the surface of the mantle, in patterns that seem almost too beautiful to be real. Some clams are predominantly blue, their mantles glowing with an otherworldly cerulean light. Others are green, speckled with black or brown spots that create intricate mosaics. Still others are yellow or orange, their tissues glowing warmly in the tropical sun. And remarkably, even individuals of the same species living in the same location can look completely different from one another. One clam might be turquoise with yellow spots. Another might be emerald green with black specks. A third might resemble ink flowing through a sky blue river or a sunset melting into the sea. The variation is extraordinary, and it's one of the things that makes giant clams so captivating to divers and scientists alike. For a long time, researchers believed that these colors were produced by the zooxanthellae, the symbiotic algae that live inside the clam's tissues. After all, zooxanthellae contain photosynthetic pigments, and it seemed logical that these pigments might contribute to the clam's overall coloration. But as scientists looked more closely, they realized that something else was at work. The zooxanthellae do contribute a background color, typically a brownish or golden hue, but they don't produce the brilliant blues, greens, and purples that make giant clams so striking. Those colors come from something entirely different. They come from specialized cells called iridocytes, and these cells are doing something remarkable. Iridocytes are found in the outer layer of the mantle tissue, the part that is exposed when the clam opens its shell. These cells contain stacks of thin, regularly arranged platelets made of proteins and crystals, often including guanine, the same reflective compound found in fish scales. These platelets are arranged in layers, alternating between materials with high and low refractive indices, much like the layers in a soap bubble or an oil slick. When light hits these structures, it doesn't simply pass through or get absorbed. Instead, it undergoes a process called structural coloration. The light waves interact with the layers, and depending on the thickness of the layers and the spacing between them, certain wavelengths of light are reflected back while others are allowed to pass through. This creates the intense iridescent colors that we see. What makes this even more fascinating is that different iridocytes produce different colors depending on the precise structure of their internal platelets. Blue iridocytes have thinner layers that reflect shorter wavelengths of light. Green iridocytes have slightly thicker layers. Yellow and red iridocytes have even thicker layers still. By varying the thickness of these internal structures at the nanoscale level, giant clams can produce a full spectrum of colors. And remarkably, these colors follow a principle similar to the way digital screens create color. Just as a computer monitor uses red, green, and blue pixels to generate all the colors you see, giant clams use red, green, blue, and yellow iridocytes scattered across their mantles to create their complex multicolored patterns. Scientists have even described this as biological RGB pixelation, a natural version of the technology we use in our screens every day. But iridocytes do more than just make giant clams beautiful. They serve a critical functional role in the clam's survival. These cells don't just reflect light randomly. They're positioned strategically to manage the light that enters the clam's tissues. Some of the light is reflected backward, creating the colors we see, but some of it is scattered forward and sideways, channeled deeper into the mantle tissue, where the zooxanthellae live. This forward scattering of light is incredibly important because it ensures that the symbiotic algae, which are packed into columns within the tissue, receive the light they need to photosynthesize efficiently. At the same time, the backward reflection protects the clam from harmful wavelengths of light, particularly in the ultraviolet range, which could damage delicate tissues or overwhelm the zooxanthellae. The iridocytes act as both a light distributor and a protective shield, optimizing the amount of useful light that reaches the algae while minimizing potential harm. Recent research has shown just how efficient this system is. Scientists modeled the arrangement of zooxanthellae and iridocytes in giant clam tissue and found that the clams achieve a quantum photon-to-electron conversion efficiency of up to 67%. To put that in perspective, that's comparable to some of the best solar panels humans have ever created. Giant clams are in essence biological solar collectors, and they've been refining this technology for millions of years. The vertical columns of zooxanthellae, combined with the light channeling properties of the iridocytes, create a system that is extraordinarily effective at capturing and using sunlight. This efficiency is part of what allows giant clams to grow so large in waters that are often nutrient poor. They're not relying solely on filtering food from the water, they're farming light itself. The colors of a giant clam can also change slightly over the course of its life. Young clams, those that have recently settled and are just beginning to develop their adult form, often display green iridocytes first. As they grow, other colors begin to appear, and the patterns become more complex. In some species, blue iridocytes seem to be dominant in the early stages of color development, and these blue cells may eventually be joined by yellow, green, or even red iridocytes as the clam matures. The exact color pattern that an individual clam develops seems to be influenced by a combination of genetics and environmental factors, though the mechanisms are not yet fully understood. What is clear is that the colors are not random. They are carefully constructed at the cellular level, the result of precise biological processes that build and maintain these nanoscale structures throughout the clam's life. Interestingly, the color of a giant clam is also an indicator of its health. When a clam is healthy, its mantle is vibrant and richly colored. The zooxanthellae are thriving, the iridocytes are functioning properly, and the entire system is in balance. But when a clam is stressed, when the water becomes too warm or the conditions deteriorate, the zooxanthellae can be expelled from the tissues in a process similar to coral bleaching. When this happens, the mantle loses much of its color, becoming pale or even bright white as the underlying tissue is exposed. A bleached giant clam is a clam in distress, a clam that has lost the symbiotic partners that provide most of its energy. If conditions don't improve, the clam may not recover. So when you see a giant clam in its full glory, mantle spread wide and colors shimmering in the sunlight, you're not just looking at a beautiful animal. You're looking at a finely tuned biological machine, a partnership between animal and algae, a system of light management and energy production that rivals anything humans have designed. You're looking at millions of years of evolution distilled into a single stunning moment of color on the reef floor. And beneath those colors, invisible to the casual observer, is an entire world of microscopic architecture, of photosynthetic algae, arranged in columns, of iridocytes stacked in precise layers, of light being channeled, reflected, and harvested with extraordinary efficiency. It's a reminder that beauty in nature is rarely just about appearance. It's almost always about function as well, about survival, about adaptation, about the intricate ways that life finds to thrive in even the most challenging environments. The relationship between a giant clam and its zooxanthellae is one of the most successful partnerships in the ocean. It's a mutualistic symbiosis, a relationship in which both parties benefit, and it's the key to understanding how giant clams can grow so large in environments where food is often scarce. Zooxanthellae are single-celled dinoflagellates, tiny photosynthetic organisms that belong to the family Symbiotic. They're closely related to the zooxanthellae that live inside corals, and in fact, some species of zooxanthellae can form partnerships with both giant clams and reef-building corals. These algae are remarkable in their own right. They contain chlorophyll and other pigments that allow them to capture sunlight and convert it into chemical energy through photosynthesis. But unlike free-living algae that drift in the water column, zooxanthellae have evolved to live inside the tissues of host animals, protected from predators and provided with a stable environment. In giant clams, zooxanthellae reside in the mantle tissue, the soft, fleshy part of the clam that extends beyond the edges of the shell when the clam opens. They're not scattered randomly. Instead, they're organized into specialized structures called zooxanthella tubules, narrow channels that extend from the clam's stomach out toward the edges of the mantle. These tubules are lined with zooxanthellae, packed tightly together in vertical columns that maximize their exposure to light. The arrangement is deliberate and highly efficient. By organizing the algae in this way, the clam ensures that as much light as possible is captured and converted into energy. The process works beautifully. During the day, when sunlight is abundant, the giant clam opens its shell and spreads its mantle wide, exposing the zooxanthellae to the light. The algae begin photosynthesizing, using the energy from sunlight to convert carbon dioxide and water into sugars, glycerol, and amino acids. These compounds are then shared with the clam, passing from the algae into the surrounding tissue where they fuel the clam's metabolism and growth. In return, the clam provides the algae with a safe home, access to sunlight, and a steady supply of nutrients, particularly nitrogen and phosphorus, which the clam produces as metabolic waste. It's a closed loop, a balanced exchange that benefits both partners. The amount of energy that zooxanthellae provide to their host is staggering. In a healthy giant clam, somewhere between 65 and 70% of the clam's nutritional needs are supplied by these symbiotic algae. That means the clam is getting the majority of its food, not by filtering particles from the water, but by farming the light that falls on its mantle. This is what allows giant clams to grow to such impressive sizes even in the clear, nutrient-poor waters of tropical reefs. They're not competing with other filter feeders for plankton. They're tapping into a nearly limitless resource, the sun. But giant clams are not entirely dependent on their zooxanthellae. They are also filter feeders, and they do consume plankton and other small particles from the water. The clam draws water in through an incurrent siphon, passes it over its gills, and filters out tiny organisms and organic matter before expelling the water through an excurrent siphon. In very small juvenile clams, those that have only recently settled and are just beginning to establish their symbiosis, filter feeding provides a significant portion of their nutrition, sometimes as much as 65%. But as the clam grows and the population of zooxanthellae increases, the balance shifts. Larger clams rely much less on filtering, with some estimates suggesting that filter feeding provides only about a third of their nutritional needs in adult clams. The rest comes from the partnership with the algae. This dual mode of nutrition gives giant clams a remarkable degree of flexibility. If conditions are good and light is abundant, they can rely heavily on their zooxanthellae and reduce their dependence on filtering. If light levels drop or the algae are stressed, the clam can increase its filter feeding activity to compensate. This adaptability is part of what has allowed giant clams to survive and thrive across such a wide range of environments. But it also means that threats to either feeding mode, whether it's poor water quality that reduces plankton availability or increased water temperatures that harm the zooxanthellae, can have serious consequences for the clam's health and survival. The symbiosis begins early in life, but it is not present at birth. Giant clam larvae are born without zooxanthellae. They spend their first few days as free-swimming planktonic organisms, drifting in the water column and relying entirely on a yolk sac and filter feeding to sustain themselves. But within about a week, the larvae must acquire zooxanthellae if they are to survive. They do this by capturing free-living zooxanthellae cells from the surrounding water, ingesting them through their developing digestive system. Once inside, the algae are not digested. Instead, they are transported to the stomach and then into the developing zooxanthellae tubules, where they begin to multiply and establish themselves. This process of infection, as it's sometimes called, is critical. If a larva fails to acquire zooxanthellae within the first 2 weeks of life, it will not survive to adulthood. The timing has to be right, and the right species of zooxanthellae need to be present in the water. Researchers have discovered that giant clam larvae are not particularly picky about which species of zooxanthellae they take in. Larvae exposed to different clades of Symbiodiniaceae, ranging from clade A to clade E, have successfully formed symbioses and gone on to develop normally. This flexibility may be advantageous, allowing clams to establish partnerships with whatever zooxanthellae are available in their immediate environment. However, there is also evidence that different clades of zooxanthellae can affect the clam's development and physiology in subtle ways, influencing things like growth rate, stress tolerance, and even color patterns. Interestingly, zooxanthellae can also be transmitted through an unexpected route: giant clam feces. Research has shown that when giant clams expel waste, some of the zooxanthellae in their tissues are released alive and still viable. These expelled algae can then be taken up by other organisms, including juvenile giant clams that are still in the process of establishing their own symbiotic populations. Fecal pellets from giant clams have been shown to serve as effective vectors for zooxanthellae transmission, and in some experiments, larvae exposed to intact fecal pellets from other clam species showed even higher rates of successful symbiosis than those exposed to freshly isolated algae. It's a fascinating example of how ecosystems recycle and share resources in ways that we are only beginning to understand. Once the symbiosis is established, it becomes a defining feature of the clam's life. The zooxanthellae multiply, filling the tubules and spreading throughout the mantle tissue. As the clam grows, so does the population of algae. In a mature adult giant clam, there can be billions of zooxanthellae cells living within the mantle, all photosynthesizing, all producing energy, all contributing to the clam's survival. The density of these algae is extraordinarily high, far higher than what you would find in free-living populations in the water. The clam has essentially created an internal farm, a controlled environment where the algae can thrive and produce food at rates that would be impossible in the open ocean. The efficiency of this system has captured the attention of scientists interested in renewable energy and biotechnology. The way giant clams manage light, the way they cultivate algae, the way they convert sunlight into usable energy with such high efficiency, all of these are being studied as potential models for human applications. Could we design solar panels that mimic the light channeling properties of iridocytes? Could we develop bioreactors that use similar principles to cultivate algae for biofuel production? These are questions that researchers are actively exploring, and giant clams are providing valuable insights. They are, in a very real sense, living laboratories, creatures that have spent millions of years perfecting the art of solar energy capture. And they've done it without fossil fuels, without complex machinery, without any of the tools that humans rely on. They've done it simply by evolving, by adapting, by forming a partnership with microscopic algae and building structures at the nanoscale that can manipulate light with extraordinary precision. The story of a giant clam begins long before it settles on the reef. It begins as a single fertilized egg, drifting in the open ocean, invisible to the naked eye. Giant clams reproduce through a process called broadcast spawning, in which both eggs and sperm are released into the water column where fertilization occurs externally. It's a strategy used by many marine invertebrates, and it relies on sheer numbers to ensure success. A single adult giant clam, when the conditions are right, can release hundreds of millions of eggs in a single spawning event. The numbers are staggering, almost incomprehensible. One study reported that an adult Tridacna gigas released more than 500 million eggs during a spawning event. That's 500 million potential offspring from a single individual, all released in the span of a few hours. But why so many? The answer is survival. The ocean is a dangerous place for a tiny, defenseless larva. Predators are everywhere, from planktonic jellyfish to filter-feeding fish. Currents can carry larvae far from suitable habitat. Changes in water temperature or chemistry can kill them. The vast majority of eggs and larvae will not survive to adulthood. By producing such enormous numbers, giant clams increase the odds that at least a few will make it through the gauntlet of early life and settle successfully on the reef. The timing of spawning is carefully regulated. Giant clams are sensitive to environmental cues, particularly the lunar cycle. Spawning tends to occur around the time of the full moon or new moon, when tides are strongest. These spring tides may help disperse eggs and larvae more widely, increasing the chances that some will find suitable habitat. There's also evidence that spawning is synchronized among individuals in a population, with many clams releasing their gametes at roughly the same time. This synchronization is thought to be triggered by chemical signals in the water, pheromones that one clam releases to signal its readiness to spawn, prompting others nearby to do the same. This coordinated release increases the likelihood of successful fertilization, since eggs and sperm from different individuals will be present in the water at the same time. Giant clams are hermaphrodites, meaning each individual produces both eggs and sperm. However, they cannot fertilize their own eggs. Instead, they release sperm first, followed by eggs, a strategy that helps prevent self-fertilization and ensures genetic diversity. The eggs are relatively large for marine invertebrates, about 100 micrometers in diameter, roughly the width of a human hair. Once released, they must be fertilized within a matter of hours, or they will die. Sperm, meanwhile, are released in vast clouds that drift through the water. When sperm and eggs meet, fertilization occurs, and the egg begins to divide. Within about 12 hours, the fertilized egg has developed into a free-swimming larva called a trochophore. This is the first mobile stage of the clam's life, a tiny ciliated creature that swims weakly through the water column using bands of hair-like cilia. The trochophore larva is transparent and barely visible, but it's already beginning to develop the structures that will define its adult life. By about 24 hours after fertilization, the larva enters the veliger stage, marked by the appearance of a small two-part shell and a ciliated structure called the velum, which it uses for both swimming and feeding. The veliger larva is still planktonic, drifting with the currents and feeding on microscopic algae and organic particles that it captures from the water. This planktonic stage lasts for about a week, sometimes a little longer. During this time, the larva is at the mercy of the ocean. Currents can carry it tens or even hundreds of miles from where it was spawned. Predators hunt it constantly. It must find food, avoid being eaten, and survive in an environment that can change rapidly. But if it succeeds, if it manages to stay alive for those critical first days, it will reach the next stage of its life, settlement. At around 7 to 9 days after fertilization, the veliger larva begins to develop a foot, a muscular organ that will allow it to crawl and eventually anchor itself to the substrate. This marks the transition to the pediveliger stage, the final planktonic phase. The Pediveliger larva is still capable of swimming, but it also begins to explore the seafloor, testing surfaces, searching for the right place to settle. This is one of the most important decisions the clam will ever make, because once it settles, it cannot move. It will spend the rest of its life in that one spot. The larva is searching for specific conditions. It needs a hard substrate, something it can attach to, whether that's coral rock, dead coral, sand mixed with rubble, or even the shells of other organisms. It needs good light, because without light, the zooxanthellae it will soon acquire cannot photosynthesize. It needs stable conditions, a place that won't be buried by sediment or swept away by strong currents. And it seems to prefer areas where other giant clams are already present, possibly because the presence of adults signals that the habitat is suitable. Young clams have been observed to exhibit clumping behavior, settling near one another in groups. This may provide some protection from predators, or it may simply be a response to chemical cues in the water that indicate a favorable environment. Once the larva finds a suitable spot, it undergoes metamorphosis. The foot secretes byssal threads, strong fibrous strands that anchor the clam to the substrate. The shell begins to grow more rapidly. The velum, the swimming organ, is lost. The internal anatomy reorganizes dramatically. The clam is no longer a drifting larva. It is now a juvenile, a spat, a miniature version of the adult it will one day become. At this stage, it is incredibly vulnerable. It's small, barely visible, and it has not yet acquired zooxanthellae. It must rely entirely on filter feeding to survive, and many do not. Mortality is extremely high in the first few weeks after settlement. Predators, including fish, crabs, and octopuses, consume vast numbers of juvenile clams. Sediment can smother them. Poor water quality can stress them beyond recovery. Those that survive this critical period are the lucky ones, the tiny fraction of the millions of eggs that were released. But survival brings rewards. As the juvenile clam grows, it begins to acquire zooxanthellae from the water, ingesting them and allowing them to colonize its developing mantle tissue. Within a few weeks, the symbiosis is established, and the clam begins to rely less on filter feeding and more on the energy provided by its algal partners. The shell thickens and hardens. The mantle develops its first iridocytes, and the clam begins to show color, usually starting with green and gradually adding other hues as it matures. Growth is slow at first, but it accelerates as the clam reaches a few centimeters in size. In ideal conditions, with plenty of light and clean water, a juvenile clam can grow several centimeters per year. By the time it's about 2 years old, it may be the size of a fist. By 5 years, it could be the size of a dinner plate, and by 10 or 20 years, it may have grown into a true giant, a creature weighing dozens or even hundreds of pounds, anchored firmly to the reef, opening its shell each day to bask in the sunlight. Throughout this journey, from drifting egg to settled juvenile to massive adult, the clam remains in constant contact with the reef around it. It is shaped by the currents, the light, the temperature, the chemistry of the water. It is part of a larger community, surrounded by corals and fish and countless other organisms. And as it grows, it begins to contribute to that community in ways that go far beyond its own survival. Giant clams are not passive residents of the reef. They are active participants, ecosystem engineers that shape the environment around them and provide benefits to a wide range of other species. Their ecological significance has only recently begun to be fully appreciated, and as researchers dig deeper into the roles that giant clams play, it becomes clear that these creatures are far more important than their sedentary lifestyle might suggest. One of the most obvious contributions that giant clams make to the reef is structural. Their shells, massive and heavy, become part of the reef framework. Over time, as clams die and their shells accumulate, they are incorporated into the substrate, adding to the physical structure of the reef. This calcium carbonate contributes to the growth and stability of the entire reef system, helping to build up the three-dimensional complexity that is so important for coral reef biodiversity. In areas where giant clams are abundant, the reef floor is literally built in part from their shells, layers of ancient clams forming a foundation for the living reef above. But living giant clams also contribute to the reef's structure. The shells of adult clams provide hard surfaces for colonization by other organisms. Algae, sponges, barnacles, small corals, and a variety of other encrusting species grow on the outside of clam shells, creating miniature ecosystems on the clams themselves. These epibionts add to the overall biodiversity of the reef, and they also contribute to the clam's camouflage, making it harder for predators to distinguish the clam from the surrounding substrate. Inside the mantle cavity, in the space between the clam's shell and its soft tissues, a variety of commensal organisms take up residence. Small shrimp, crabs, and fish use the clam's shell as shelter, hiding from predators in the relative safety of the clam's interior. Some of these organisms are obligate commensals, species that live exclusively in association with giant clams and are found nowhere else. The clam becomes a habitat, a home, a refuge for life that would otherwise have no place to go. The topographic complexity that giant clams add to the reef is also important. A reef covered with giant clams is not flat and uniform. It's a landscape of bumps and ridges, of crevices and overhangs, of spaces where water flow is slowed and where sediment can settle. This heterogeneity creates more niches, more microhabitats where different species can live. Fish, in particular, benefit from this complexity. Juvenile fish use the spaces around and between giant clams as nurseries, places where they can hide from larger predators while they grow. Studies have shown that reefs with abundant giant clams support higher densities of juvenile fish than reefs where clams are scarce. The clams in effect act as ecosystem engineers, modifying the physical environment in ways that benefit other species. But the contributions of giant clams go beyond structure. They also play important roles in nutrient cycling, the movement and transformation of essential elements like nitrogen and phosphorus through the reef ecosystem. Giant clams, through their metabolic processes, release nutrients back into the water. The zooxanthellae produce waste products that contain nitrogen, and the clam itself excretes phosphorus and other compounds. These nutrients are quickly taken up by other organisms, including corals, algae, and phytoplankton. In nutrient-poor tropical waters, where essential elements are often in short supply, this recycling is critically important. Giant clams act as reservoirs and distributors of nutrients, helping to maintain the productivity of the entire reef. There's also evidence that giant clams contribute to water quality through their filter feeding activity. Although adults rely primarily on their zooxanthellae for nutrition, they still filter water through their gills, removing particulates and organic matter. In dense populations, this filtering activity can have a measurable impact on water clarity. Clearer water allows more light to penetrate to the reef, benefiting photosynthetic organisms including corals and seagrasses. It's a subtle effect, but it's part of the larger web of interactions that keeps the reef healthy and balanced. Another fascinating aspect of giant clams' ecological role involves their zooxanthellae. When giant clams are stressed, or even during normal metabolic processes, they sometimes expel live zooxanthellae into the water. These expelled algae can be taken up by other organisms, including corals and juvenile clams that are establishing their own symbiosis. In this way, giant clams may act as reservoirs and sources of zooxanthellae for the broader reef community. After mass bleaching events, when corals have lost their own symbiotic algae, the zooxanthellae released by giant clams might help corals recover more quickly by providing a readily available source of symbionts. This idea is still being explored, but it suggests that giant clams may play a role in maintaining the resilience of reef ecosystems in the face of disturbance. Giant clams also produce gametes, eggs, and sperm that are released into the water during spawning. While most of these gametes are intended for reproduction, many are never fertilized, and instead they become food for other organisms. Opportunistic feeders, including fish, invertebrates, and even other clams, consume these nutrient-rich particles. The same is true for the fecal pellets that clams produce. These waste products, which contain both organic matter and live zooxanthellae, are eaten by a variety of reef organisms. In this way, giant clams contribute directly to the food web, providing energy and nutrients that flow through the ecosystem. When a giant clam dies, its contribution to the reef doesn't end. The soft tissues of the clam are quickly consumed by scavengers, including fish, crabs, octopuses, and sea stars. These predators and scavengers gain a substantial meal, a concentrated source of protein that can sustain them for days. The shell, meanwhile, persists. It becomes part of the reef substrate, providing habitat for new generations of organisms. Over time, the shell may be broken down by boring organisms, by waves, by the slow processes of erosion and dissolution. But even in death, the clam continues to shape the reef, its calcium carbonate skeleton a lasting contribution to the structure of the ecosystem. The more we learn about giant clams, the more we realize that their loss would have cascading effects throughout the reef. If giant clams disappear, the reef loses a source of structure, a contributor to nutrient cycling, a reservoir of zooxanthellae, a refuge for juvenile fish, and a node in the food web. The reef becomes less complex, less diverse, less resilient. And that is why the conservation status of giant clams is so concerning. Because in many parts of the Indo-Pacific, giant clams are disappearing. Their populations have declined dramatically over the past century, and in some places they have vanished entirely. The decline of giant clams is driven primarily by human activity. For centuries, people have harvested giant clams for food. The adductor mussel, in particular, is prized as a delicacy, and the shells have been used for everything from building materials to decorative objects. In many coastal communities, giant clams have been an important source of protein, a reliable food source that could be harvested from the reef with relatively simple tools. But as human populations have grown, as fishing technologies have improved, and as trade networks have expanded, the pressure on giant clams has intensified. Overfishing has become a serious problem in many regions. The life history of giant clams makes them particularly vulnerable to overharvesting. They grow slowly, taking many years to reach reproductive maturity. Some species don't begin reproducing until they're 10 or 15 years old, and they may not reach their full size until they're several decades old. They are sessile, unable to flee from humans or move to safer areas. They are also highly visible when their mantles are open, making them easy targets for fishers. Once a population is depleted, recovery can take a very long time, decades or even centuries, because the remaining clams have to produce enough offspring to repopulate the reef, and the larvae have to successfully settle and survive to adulthood. In areas where giant clams have been heavily harvested, populations have collapsed, and in some cases they have gone locally extinct. The aquarium trade has also contributed to the decline of some species. Smaller, more colorful species of giant clams are highly sought after by hobbyists who want to keep them in home aquariums. While captive breeding programs have reduced the pressure on wild populations to some extent, there is still demand for wild-caught specimens, and illegal harvesting continues in some areas. The trade in shells, both for decoration and for use in jewelry and other products, has also taken a toll. Even though international trade in some giant clam species is regulated under CITES, the Convention on International Trade in Endangered Species, enforcement is difficult and illegal trade persists. Climate change is adding another layer of threat to giant clams. Rising ocean temperatures are causing more frequent and severe bleaching events, not just in corals but in giant clams as well. When water temperatures rise above a certain threshold, the zooxanthellae in the clam's tissues become stressed and are expelled, a process similar to coral bleaching. A bleached clam loses most of its color, and more importantly, it loses its primary source of nutrition. If the temperatures don't drop and the clam can't re-establish its symbiosis with new zooxanthellae, it will starve. Mass bleaching events have been documented in giant clam populations, and there's concern that as the ocean continues to warm, these events will become more common. Ocean acidification is another consequence of climate change that threatens giant clams. As the ocean absorbs more carbon dioxide from the atmosphere, the water becomes more acidic, and this makes it harder for organisms to build and maintain calcium carbonate structures. Giant clams, which rely on their thick shells for protection, may find it increasingly difficult to grow and repair their shells in a more acidic ocean. Studies have shown that juvenile giant clams exposed to elevated carbon dioxide levels experience reduced growth rates, and their shells are thinner and more fragile. If ocean acidification continues to worsen, it could have serious consequences for giant clam populations, particularly in their vulnerable early life stages. Habitat destruction is also a major threat. Coral reefs, the primary habitat for giant clams, are declining worldwide due to a combination of factors including overfishing, pollution, coastal development, and destructive fishing practices. When the reef is damaged or destroyed, giant clams lose the substrate they need to settle on, the shelter they need to survive, and the water quality they need to thrive. In areas where reefs have been heavily degraded, giant clam populations have suffered accordingly. The cumulative impact of these threats has been devastating. In October 2024, the International Union for Conservation of Nature (IUCN) updated the conservation status of Tridacna gigas, the true giant clam, from vulnerable to critically endangered, the highest level of threat before extinction in the wild. The assessment, led by researchers at the University of Colorado Boulder and the National University of Singapore, found that the population of Tridacna gigas has declined by more than 80% over the past century. The species is now locally extinct in many regions where it was once common, including parts of Malaysia, the Philippines, and other areas of the Indo-Pacific. Other species of giant clams have also seen their conservation statuses upgraded, with several now listed as endangered or vulnerable. In July 2024, the National Oceanic and Atmospheric Administration (NOAA) in the United States proposed listing 10 species of giant clams under the Endangered Species Act. If approved, this would provide legal protection for these species in U.S. waters and would prohibit the trade in their products, including meat, shells, and pearls. The proposal is part of a broader effort to protect giant clams and raise awareness of the threats they face. But legal protections alone are not enough. Effective conservation requires a combination of strategies, including marine protected areas where fishing is restricted, restoration programs that breed and release juvenile clams back onto the reef, community-based management that involves local people in conservation efforts, and continued research to better understand the biology and ecology of these remarkable creatures. There is some cause for hope. Conservation efforts are underway in many parts of the Indo-Pacific. In the Philippines, scientists have successfully bred giant clams in hatcheries and released them onto degraded reefs. Studies have shown that restocked individuals can survive and reproduce, and their offspring have dispersed to nearby areas, helping to rebuild local populations. Similar programs are operating in Palau, Fiji, Guam, and other island nations. These efforts are labor-intensive and expensive, but they demonstrate that recovery is possible if resources are invested and if local communities are engaged in the process. There's also growing recognition that giant clams are not just beautiful or ecologically important, but that they may also play a role in climate regulation, like corals. Giant clams contribute to carbon sequestration through the process of calcification. When they build their shells, they incorporate carbon into calcium carbonate, effectively locking it away in solid form. While the amount of carbon stored in an individual clam is small, the cumulative effect of large populations of giant clams across the Indo-Pacific could be significant. Researchers are exploring ways to enhance the carbon sequestration potential of giant clams through innovative approaches to reef restoration, and there's hope that protecting and restoring giant clam populations could contribute, even in a small way, to efforts to mitigate climate change. But time is running out. Giant clams are disappearing faster than they can recover, and if current trends continue, some species may be lost forever within our lifetimes. That would be a tragedy not only for the clams themselves, but for the reefs they inhabit, the communities that depend on them, and for all of us who are enriched by the knowledge that such extraordinary creatures exist in the world. One of the most remarkable things about giant clams is their mastery of light. They are in many ways biological solar panels, organisms that have evolved to capture and use sunlight with an efficiency that rivals or even exceeds the best technology humans have created. The secret to this efficiency lies in the intricate architecture of their mantle tissue, in the arrangement of zooxanthellae and iridocytes, and in the way these structures work together to maximize the amount of useful light that reaches the photosynthetic algae. When sunlight strikes the surface of a giant clam's mantle, it encounters the iridocytes first. These specialized cells, with their stacks of reflective platelets, don't simply absorb or transmit the light uniformly. Instead, they manipulate it in sophisticated ways. Some of the light is reflected backward, creating the brilliant colors that we see and protecting the underlying tissues from harmful wavelengths. But a significant portion of the light is scattered forward, channeled deeper into the mantle tissue, in a process called forward scattering. This forward scattered light is directed toward the columns of zooxanthellae, ensuring that the algae receive the light they need to photosynthesize efficiently. The zooxanthellae themselves are arranged in vertical columns, a configuration that maximizes their exposure to light while minimizing the amount of space they occupy. Think of them as tiny living solar arrays, each algal cell packed with chlorophyll and other photosynthetic pigments, each one capturing photons and converting them into chemical energy. The vertical arrangement ensures that light can penetrate deep into the tissue, reaching algae that would otherwise be shaded by those above them. The iridocytes help by scattering light laterally as well as vertically, so that even algae in the deeper layers receive enough illumination to function. Recent research has modeled this system in detail, using sophisticated computer simulations to understand exactly how light moves through the clam's mantle tissue. What these models have revealed is astonishing. The combination of vertical algal columns and light-scattering iridocytes creates a quantum photon-to-electron conversion efficiency of up to 67%. To put that in perspective, most commercial solar panels have efficiencies in the range of 15 to 20%, with the very best reaching around 25 to 30% under ideal conditions. Giant clams are achieving efficiencies that are more than double that, and they're doing it with entirely biological materials, structures that are grown and maintained by the clam itself. This extraordinary efficiency is what allows giant clams to thrive in environments where food is scarce. The tropical waters where they live are often described as marine deserts, beautiful to look at, but poor in nutrients and plankton. For most filter feeders, these waters are challenging, forcing them to work constantly to extract enough food from the water to survive. But giant clams don't have that problem. They're not relying on filtering plankton for most of their nutrition. They're farming sunlight, and sunlight is abundant in the shallow, clear waters of the reef. Every day, as long as the clam opens its shell and spreads its mantle, it's collecting energy, converting light into sugars and other compounds that fuel its growth and metabolism. It's a nearly inexhaustible resource, and giant clams have evolved to exploit it with remarkable success. The implications of this efficiency extend beyond the clams themselves. Scientists and engineers are studying giant clams as models for improving solar energy technology. The way that iridocytes manipulate light, the way they scatter and channel photons to maximize energy capture, could inspire new designs for solar panels and bioreactors. Researchers are exploring whether the principles used by giant clams could be applied to human-made systems, creating artificial structures that mimic the light-scattering properties of iridocytes to improve the performance of photovoltaic cells or algae-based biofuel production systems. The clams have had millions of years to perfect their technology, and we're only now beginning to understand just how sophisticated it is. But the efficiency of giant clams is not just about capturing light, it's also about managing it, about ensuring that the algae get the right amount and the right wavelengths of light without being overwhelmed or damaged. Too much light, particularly in the ultraviolet and high-energy blue wavelengths, can actually harm photosynthetic organisms, causing oxidative stress and damage to cellular structures. Giant clams manage this risk through the protective properties of their iridocytes. The backward reflection of light, the same process that creates the clam's beautiful colors, also acts as a shield, reflecting harmful wavelengths away from the tissues and preventing them from reaching the zooxanthellae. It's a delicate balance, capturing as much useful light as possible while minimizing the potential for damage, and giant clams have achieved this balance with extraordinary precision. The colors themselves are part of this light management system. Blue iridocytes, for example, reflect blue light backward while allowing red and green wavelengths to pass through. Green iridocytes reflect green light and transmit others. By having a mix of different colored iridocytes distributed across the mantle, giant clams can fine-tune the spectrum of light that reaches the zooxanthella, optimizing conditions for photosynthesis while protecting against excess light. It's a dynamic system, one that responds to changes in light intensity and quality, ensuring that the algae are always working at peak efficiency. Giant clams are often compared to corals because both organisms host zooxanthellae and both play important roles in reef ecosystems. But there are some key differences in how they manage their symbiotic relationships. Corals host zooxanthellae intracellularly, meaning the algae live inside the coral's cells. Giant clams, on the other hand, host their zooxanthellae extracellularly, in specialized tubules that are separate from the clam's cells. This arrangement gives giant clams more control over the light environment and allows them to pack algae into denser concentrations. It also means that giant clams can potentially expel and replace zooxanthellae more easily than corals can, giving them some additional resilience in the face of environmental stress. In addition to their role in energy capture, giant clams are also important as ecosystem engineers in more subtle ways. They influence nutrient cycling not just through their own metabolic processes, but through the entire community of organisms that live in and on them. The zooxanthellae, the commensal shrimp and crabs, the epibiontic algae and sponges. All of these organisms are consuming, excreting, growing, and dying, and all of these processes contribute to the flow of nutrients through the reef. Giant clams are hubs of activity, nodes in a complex web of interactions that keeps the reef functioning. They also contribute to the health of the reef through their role in sediment dynamics. The shells of giant clams, particularly those of larger species, can trap sediment and organic matter, creating microhabitats where other organisms can settle and grow. This trapped sediment can be colonized by bacteria and algae, which in turn provide food for small invertebrates. The spaces around the clam's shell can become refuges for juvenile organisms, places where they can hide from predators and find food. In this way, giant clams help to structure the reef, creating patches of habitat that would not exist without them. The relationship between giant clams and their zooxanthellae is also a powerful example of mutualism, a type of symbiosis in which both partners benefit. It's a reminder that cooperation, not just competition, is a fundamental force in evolution. The clam and the algae have co-evolved over millions of years, each shaping the other, each adapting to maximize the benefits of the partnership. The clam has evolved structures like iridocytes and zooxanthellae tubules that optimize conditions for the algae. The algae in turn have evolved to thrive in the specific environment that the clam provides, producing more energy and growing more rapidly than they could in the open ocean. It's a win-win relationship, one that has allowed both partners to achieve things that neither could accomplish alone. For centuries, giant clams have been the subject of myths and legends, particularly in the South Pacific and Southeast Asia, where they are most abundant. Sailors, divers, and fishers told stories of man-eating clams, enormous creatures that could trap an unwary swimmer in their shells and hold them underwater until they drowned. These legends have persisted for hundreds of years, passed down through generations, and even appearing in modern adventure stories and films. But the truth is far less sinister. Giant clams are not dangerous to humans. In fact, they are among the most harmless creatures in the ocean. The myth of the man-eating clam likely arose from a misunderstanding of how giant clams move. When a clam senses a disturbance, such as a shadow passing overhead or a sudden change in light, it may close its shell in a defensive response. The adductor muscle contracts, pulling the two halves of the shell together. But this process is slow, taking several seconds to complete. It's not a rapid snap like the jaws of a trap. A human diver would have to deliberately place a limb inside the clam's shell and hold it there while the clam slowly closed, and even then, the clam is not capable of exerting enough force to cause serious injury. There has never been a single documented case of a human being killed or even seriously injured by a giant clam. The stories are fiction, a product of imagination and perhaps a healthy respect for the ocean's mysteries. In reality, giant clams are timid creatures. If you approach one while diving, it will often close its shell, retreating into the safety of its calcium carbonate fortress. If you're patient and wait quietly, it will eventually reopen, extending its mantle back into the light. They are not aggressive, not territorial, not dangerous. They are simply trying to survive, and they've evolved to retreat from anything that might pose a threat. But while giant clams don't eat people, they do produce something that has fascinated humans for a very long time: pearls. Like other bivalves, giant clams can form pearls when an irritant, such as a grain of sand or a parasite, becomes lodged in their tissues. In response, the clam coats the irritant with layers of calcium carbonate, gradually building up a smooth, rounded structure. Over time, this can result in a pearl. Giant clam pearls can be quite large, sometimes weighing several kilograms, making them among the largest pearls in the world. However, they lack the lustrous sheen of pearls produced by oysters. Giant clam pearls are typically white or off-white, with a porcelain-like appearance. They don't have the iridescent nacre that makes oyster pearls so valuable, but they are still prized by collectors for their size and rarity. In many cultures, giant clams have held spiritual and cultural significance. In some Pacific Island societies, clam shells were used as ceremonial objects, as currency, or as symbols of status and wealth. The meat of giant clams has been consumed for thousands of years, and archaeological evidence shows that people have been harvesting these creatures since prehistoric times. They appear in the art, stories, and traditions of many coastal communities, woven into the fabric of life in the tropics. Even today, in some places, giant clams are seen as symbols of abundance, fertility, and the richness of the sea. The shells themselves have been used for a wide variety of purposes. Their size and durability make them ideal for construction, and they've been used as building materials, as sinks and basins, and as decorative objects. In some places, clamshells were carved and polished to create jewelry, tools, or ceremonial items. The shells have even been used as fonts in churches, holding holy water for baptisms. This cultural importance has unfortunately contributed to the decline of giant clam populations, as demand for shells has driven over harvesting in many regions. There's also a growing appreciation for giant clams as flagship species for conservation. Their size, their beauty, and their ecological importance make them powerful symbols for the protection of coral reefs and marine biodiversity. They are charismatic in a way that many invertebrates are not, and they capture the imagination of people who might not otherwise think about the plight of reef ecosystems. Conservation organizations have used giant clams as ambassadors, drawing attention to the broader issues facing the ocean and inspiring people to take action to protect these fragile environments. The future of giant clams is uncertain, but it is not without hope. Efforts to protect and restore populations are expanding, and there's a growing recognition of the value of these creatures, not just for their ecological roles, but for the lessons they can teach us about sustainability, efficiency, and the power of cooperation. If we can successfully conserve giant clams, if we can restore their populations and protect the reefs they inhabit, it will be a victory not just for the clams, but for the entire marine ecosystem. Conservation efforts are diverse and multifaceted. In many regions, marine protected areas have been established where fishing is restricted or prohibited, giving giant clams a safe space to recover. These protected areas also benefit other reef organisms, creating refuges where biodiversity can thrive. In addition to protected areas, some countries have implemented regulations on the size and number of clams that can be harvested, and there are efforts to crack down on illegal trade in clamshells and meat. Hatchery programs have been particularly successful in several locations. Scientists have developed techniques for breeding giant clams in captivity, from spawning adult clams to raising larvae and juveniles in controlled conditions. Once the juvenile clams reach a certain size, they can be transplanted onto the reef, where they have a much higher chance of survival than wild larvae. In the Philippines, hatchery-bred clams have been released onto reefs that were once depleted, and these clams have survived, grown, and even reproduced, sending their own larvae out into the surrounding waters. It's a slow process, and it requires ongoing effort and resources, but it shows that recovery is possible. Community-based conservation is also critical. In many places, local people depend on the reef for their livelihoods, and they have a vested interest in protecting it. When communities are involved in conservation efforts, when they have a say in how resources are managed, when they benefit directly from sustainable practices, conservation is more likely to succeed. Education programs that teach people about the importance of giant clams and the threats they face can change attitudes and behaviors, turning former harvesters into protectors. Research continues to shed new light on the biology and ecology of giant clams, revealing details that were previously unknown and helping to inform conservation strategies. Scientists are studying everything from the genetics of giant clam populations to the effects of climate change on their growth and survival. They're using cutting-edge techniques like genomics and proteomics to understand how clams respond to stress, how they manage their symbiosis with zooxanthellae, and how they might adapt to changing ocean conditions. This research is not just academic, it has practical applications, helping us to identify populations that are most at risk, to develop better methods for breeding and rearing clams, and to predict how populations might respond to future environmental changes. There's also a growing interest in the potential for giant clams to contribute to carbon sequestration and climate mitigation. As the world grapples with the challenge of reducing greenhouse gas emissions and removing carbon from the atmosphere, every potential tool is being explored. Giant clams, with their ability to build calcium carbonate shells and to support healthy reef ecosystems that themselves sequester carbon, could play a small but meaningful role in these efforts. Researchers are investigating whether it's possible to enhance the carbon storage capacity of reefs by increasing the populations of giant clams and other calcifying organisms, and whether innovative approaches to reef restoration could be designed with carbon sequestration as a goal. But all of this work, All of these efforts depend on one thing: that we act quickly enough. Giant clams are disappearing fast, and the window for saving some species is closing. Every year that passes without meaningful action is a year in which more populations vanish, more reefs are degraded, more opportunities for recovery are lost. The challenges are significant, but they are not insurmountable. We have the knowledge, the technology, and the resources to protect giant clams. What we need now is the will to do so, the commitment to prioritize conservation, and the collective action of governments, organizations, and individuals working together toward a common goal. And now the waves begin to gentle, the colors begin to soften, and the light filtering down through the water grows dim. We've drifted through the world of giant clams, from the shimmering iridescence of their mantles to the intricate symbiosis that fuels their growth, from the perilous journey of a larva to the settled stillness of an adult anchored to the reef. We've explored their ecological importance, their vulnerability, and the efforts being made to save them. You've wandered among living rainbows, gazed at creatures that farm sunlight, and heard the quiet story of organisms that have been perfecting the art of survival for millions of years. You are a part of this ocean, not just an observer. The oxygen you breathe was produced in part by photosynthetic organisms in the sea. The climate that shapes your world is influenced by the health of coral reefs and the creatures that inhabit them. The giant clams resting on the reef floor, opening their shells to the sun, are connected to you through the invisible threads that link all life on Earth. They are part of the same story, the same unfolding narrative of evolution, adaptation, and survival. Tonight, as you rest, the clams rest too. The sun sets over the reef, and the light fades. The clams close their shells, drawing their mantles inward, settling into the darkness of the ocean night. Around them, the reef comes alive with nocturnal creatures, with fish and invertebrates that hunt and feed under the cover of darkness. But the clams remain still, anchored to their spots, waiting for the dawn when they will open once again and begin another day of farming light. And somewhere, perhaps far from where you are now, there is a reef where a tiny larva is drifting in the current, searching for a place to settle. If it finds the right spot, if it survives the gauntlet of predators and the challenges of its first few weeks, it will grow into a giant clam. It will spread its mantle wide, glow with impossible colors, and become part of the reef, part of the story, part of the endless cycle of life in the ocean. That larva is hope. It is the future, and it is worth protecting. If you're still awake, you can watch the next chapter now. Otherwise, I hope you sleep well and dream softly of living rainbows on the reef floor. Good night.